Here's a video with a solution to the problem from section 6.2 online homework, problem number 12, where the idea is that we answer a question in a way that applies to a family of problems rather than just a single problem. So the problem is described using a parameter. So it tells us that the region is bounded by f of x equals x and g of x equals x to the n. Let me just make that bigger. And so the first reasonable thing to do is to give ourselves some examples of that. Here's an example where we're using n equals 3. You can see the function here is the cube function. So that is just reading this problem literally, but using 3 for n. Similarly, you can see here that I'm using 4 for n for this picture. And in the bottom picture, we have n equals 14, just to see one example where the number's pretty big. So as you look across those pictures, you can see that there's more area that's being captured each time. And a function like g of x equals x to the 14th is looking more and more like it's going to sort of hug the x-axis and then come up quickly when it gets to 1, which makes sense if you think about small values of x, like x equals a half or 0.6. When you raise that to the 14th power, it makes it very, very small, very close to 0. But when you get to x equals 1, then obviously 1 to the 14th is 1. So somehow these functions with large powers have to stay down near the x-axis for a long time and then only jump up when they get near enough to 1 that these powers aren't getting washed out. And so what we'll see is our answer will bear that out. So the setup of these is really the same as for any problem. We're just going to integrate over the region, in other words, from the beginning x value to the end x value. And notice in every case, the two functions intersect at 0, 0, and 1, 1. So the region always starts at 0 and always ends at 1, which is nice because that could depend on n, but it doesn't in this problem. So the region is always between 0 and 1, and the line is always the function that's on the top. And so the top function is always x, and the bottom function is always x to the n. And so the problem will look like that regardless of what value of n we used. So in the first problem here, we would have x minus x cubed. And for this one, we would have x minus x to the 4th and x minus x to the 14th, and so on. The nice thing about our calculus rules is that we know the rule even if we don't know the power. So the antiderivative of x is just 1/2 x squared. And the antiderivative of x to the n is x to the n plus 1 times 1 over n plus 1. In fact, that's the way we typically learn the rule. When you have x to a power, its antiderivative is x to the 1 larger power, but you get a factor out in front. That's the reciprocal of that new power. So that's your antiderivative, and there's nothing in the world wrong with having an n in there. But this does have to be evaluated, and so I'm going to remind myself that when I'm plugging in my numbers in the fundamental theorem of calculus, that these original numbers on the integral are x values. Those were values along the x-axis in my problem setup. So they're not values of n, they're values of x. And so when I plug 1 in for x, I get 1/2 minus 1 over n plus 1, because 1 to any power is 1. And then I subtract the result of plugging in 0 in for x. But if I plug 0 in for x, I get 0 here, I get 0 here, and so that's wash. And so my answer is 1/2 minus 1 over n plus 1 is the area. So what that's telling me is that in this problem, where n equals 3, this area is 1/2 minus 1/4. This is 1/2 minus 1/5. This is 1/2 minus 1/15. So in every case, I could answer the area question by just plugging the value of n for that problem into this formula, and I will get the area. Notice that a side effect of this, I'm not sure if this question asks it, but other versions do, is notice that as n goes to infinity, this answer is obviously getting closer to 1/2, because when your n's get very large, this fraction, 1 over n plus 1, is getting very close to 0. When n is a million, for example, this is 1 over a million and 1. It's very, very small. So a half minus a very, very tiny number is close to a half. The interesting thing is that our picture actually bears that out, because this picture looks more and more like a triangle. The bigger the value of n, the more this thing is looking like a triangle, and a triangle with a base of 1 and a height of 1. And of course, the area of a triangle with base 1 and height 1 is a half. So we can actually see geometrically these areas getting close to a half, because the region is getting close to a triangle with area 1/2.